Hello, welcome to Chemistry Travelers. So today we are going to look into the modern periodic table where we'll be dealing with possible classification of elements that we know and also the trends shown by these elements when they are arranged periodically. Elements, as we know, they form the basis of the whole of chemistry that we learn. If we do not know the elements or their properties, it becomes really difficult to study them, right? And if these elements are randomly placed, if there is no proper manner of arrangement of these elements, it becomes even more tedious process to study them. That is when scientists decided to group these elements into some particular fashion based on their properties so that elements of similar properties are kept together and those with differences are kept apart. So the whole thing becomes a much easier process in understanding, right? And that's when, in 1913, we got the modern periodic table by Henry Moseley, which is based on the modern periodic law. He arranged the elements based on their atomic number. And using the concept of atomic number, we have been able to identify all the 118 elements that we know till date. Okay, based on the increasing order of the atomic number, starting from 1 to 118, and if you look, it goes like one, we have one here, then two, three, four, five, six. It goes on like that. And the what we can see, 57, here we have 57, up to 57, it keeps increasing and coming. After that, 58 to 71, they've kept it here. And then again, 72 onwards, it goes on like this. Then we come up to 89. After 89, the 90th element onwards is placed at the bottom here, up to 103. Then from 104 to 180, again, it goes back to the previous position. And this is how the 118 elements are placed in the modern periodic table, that is starting from hydrogen and ending with the organism. It also has grouped elements in groups and periods, that is all the 118 elements are put into 18 different groups and 7 different periods. Okay. Now, if you look into how you can represent an element, there are several ways of representing elements in the periodic table, and this is one common form of way of representing the element, that is X with a superscript A and a subscript Z, where X corresponds to the chemical symbol, the element symbol, and Z corresponds to their atomic number, which is equal to the number of protons in the atom or the number of electrons in the atom, and A corresponds to their mass number, which is equal to the sum of the number of protons and the number of neutrons. So this is one possible way of representing the elements in the periodic table. Like we have the example of oxygen with an atomic number 8 and mass number closely equal to 16, and this is how you can represent them. Or if we have scandium with atomic number 21 and mass number 44 or approximately 45, you can represent it in this way. This is just one form of representation, whereas you can actually find several other ways of representing also. Okay. Now, next thing is the state in which these elements exist. Okay, whether they are in the solid state, liquid state, or gaseous state. And most of the elements in the periodic table, almost everything, happens to be in the solid state, except the 18th group elements that we have here: helium, neon, argon, krypton, xenon, radon, organosine. These elements, and our hydrogen, then nitrogen, oxygen, fluorine, and chlorine. These are the only ones that exist in the gaseous form, and there are only two elements in the periodic table that exist in liquid state at room temperature. The one is mercury, the other one is bromine. These are the two things that exist in the liquid state. Remaining everything happens to be solid state. Okay. Next, if you classify them into metals, non-metals, or metalloids, we can see that again most of the elements in the periodic table are metals, while the complete 18th group elements, 17th group elements, and oxygen, sulfurs, and selenium from the 16th group, nitrogen and phosphorus from the 15th group, carbon from the 14th group, and hydrogen from the first group are non-metals. While we have a diagonal set of diagonal elements like boron, silicon, germanium, arsenic, and these elements, like they are the ones that are metalloids. That is, they have properties between metals. They show the properties of both metals as well as non-metals. And metals, if you consider, they're usually solids at room temperature, and they have a very high melting and boiling point, and they're good conductors of electricity and heat, and also they're malleable and ductile. That is, they can be drawn into thin sheets, or ductility means they can be drawn into thin wires. Okay. And non-metals, if you consider, usually all the non-metals are either solids or gases at room temperature, and they have very low melting and boiling points, and they are poor conductors of heat and electricity. Okay. Next is another terms, general terms that can be given to each of these groups. These groups, each of the groups, group 1 to 18, they have a particular name. Okay. And group 1 elements are generally termed as the alkali metals, and group 2 elements are generally termed as alkaline earth metals. So as we already saw in the previous slide, that group 1 and group 2 are completely metals, and they are called the alkali metals and alkaline earth metals, followed by group 3 to 12 that are termed as transition metals. All of them are the transition metals. Then we have group 13, which is icosagens. Then group 14 is crystallogens, and these are less common names. Then group 15, we have the nitrogens, and 16 is chalcogens. 17 and 18 are very common ones, halogens, and noble gases, or the inert gases that we have. Okay. And this group 13, 14, 15 and all, they're also termed as, more commonly they're known as boron family, carbon family, nitrogen family and all. Okay. And at the end, we have two periods, that is the lanthanide series and the actinide series. Lanthanide starting from cerium to lutetium, and we have another set which are termed as the actinide starting from thorium to fluorentium. Okay. And these are also termed as the inner transition elements. Similar to the transition elements, we have the inner transition elements. Okay, clear. Another classification is based on their electronic configuration. Based on where the electron, the outermost electron, gets added, they can be classified into four different groups. The first one being the S block elements with a general electronic configuration of NS1 to 2. That is, the outermost electron enter the S subshell, like hydrogen, which has a configuration 1s1, or helium, which has 1s2, lithium 1s2, 2s1, beryllium 1s2, 2s2. So these are the outermost electrons are found in the s orbital, right? They're based on their electronic configuration. Then we have the p block elements, that is group 13 to group 18. We have the p block elements with where the outermost electron enter the p subshell, that with the general configuration of ns2, np1 to 6. Boron family will have np1 in their outermost shell, and carbon will have np2, nitrogen will have np3, oxygen np4, and fluorine will be np5, and neon will have np6, right? Okay, all the p orbitals would be completely 6 electrons, will be filled with 6 electrons, right? And that's we have how we have the 18 group elements. And then we have the d block elements, which corresponds to the elements where the last electron enters the d subshell, and their general configuration is n-1d, 1 to 10. D can have a maximum of 10 electrons, right? And ns 1 to 2. Okay. And then at the bottom, we have the F block elements, the so-called inner transition elements. They are the lanthanide and the actinide series, which have a general configuration of n-2 F1 to 14, because F orbitals can have, F subshells can have a maximum of 14 electrons, and so its configuration is n-2 F1 to 14, n-1 D0 to 1, and ns2. And in all these cases, n is the principal quantum number, or we can say that it corresponds to the group in which they are present. Like when I say hydrogen 1s1, n is 1, and if I say lithium 1s2, 2s1, n is equal to 2. So based on the period number, you can have the value of n also. So this is how, based on electronic configuration, we can classify all 118 elements into 4 different blocks. Okay. So that's part 1 for periodic classification of elements, and in part 2 we'll be looking into the trends that are shown by these elements when they are arranged in a periodic manner. Thank you.